I'm Mark Cavanaugh for Cavi Coaches, and today I'm going to coach you up on rotational kinetic energy. In this video, we're going to talk about rotational kinetic energy. So what is rotational kinetic energy? Well, recall that kinetic energy is the energy of an object in motion. Thus far, we've only learned translational motion, where all the mass is moving at the same speed. So the entire mass of the object moving translationally has one kinetic energy because all the mass is moving together. But objects that rotate have a second type of kinetic energy called rotational kinetic energy. So as an object spins, it has a different type of energy. However, not all the mass of an object is moving at the same speed. So for example, a sphere rolling on a table, as it rolls, it's spinning. The mass that's closest to the center moves slower than the mass that moves on the outermost edge. So how can we calculate this kinetic energy of a rotating object? So if you recall, we had this situation where we've had a disk with a couple coins sitting on it, and we rotate those. But now let's replace those coins with rings that represent the mass of all the mass at that radius from the center. So obviously the radius inside is going to be moving slower than outside. So we're going to calculate the kinetic energies by starting first with our kinetic energy equation. That kinetic energy equals 1/2 mv squared. Now remember that this total mechanical energy is the sum of the mechanical energies, in this case kinetic. So we can sum up 1/2 all of the m individual masses times the individual velocities squared. So by summing all of those up, and then we can look and we know that the angular velocity times the radius is equal to the speed. So we can substitute in the angular velocity times the radius for our individual velocities. So we can use the individual radii for those, but we know that the angular velocity is a constant. That's the same for all mass, so we can take that out and only sum up all the things that are different, which are the masses at each radius. And we know that we've seen this term before, the sum of the individual mass times the individual radii squared. We saw that in our rotational inertia or moment of inertia video. And in fact, the sum of those is the rotational inertia or moment of inertia. So our rotational kinetic energy is equal to 1/2 I omega squared, where I is the rotational inertia or moment of inertia of each individual object. And recall, we found those values or were given those equations to calculate for different objects back in the video for rotational inertia. We're going to abbreviate rotational with ROT so we don't have to write the word rotational each and every time. So our rotational equation, kinetic energy, I 1/2 I omega squared. So we can also derive some additional equations from energy. So we know that we have our translational unit we've already finished, and now we're moving into rotational. But remember that every translational variable has a rotational equivalent. So we can recall that change in energy or work is equal to force times distance. Well, when an object is rotating, we also can have an amount of work. But the rotational equivalent of force is torque, and the rotational equivalent of distance is the angular displacement. So torque times angular displacement, or torque times theta, is going to give us the work done. Now we also know that power equals work over time, but work is force times distance, so Fd divided by t. But we also know that distance over time is velocity, so force times velocity is power. So we can do that same thing with the rotational work over time. Well, we just proved that work is torque times the angular displacement. Well, an angular displacement divided by time, well, that's going to give us the torque times the angular speed. So here's a couple other equations that we could use. They're not on our formula sheet, but they could be very easily derived from our translational equivalent. Let's talk about what causes objects to roll as they move. So rolling without slipping is a term that you're going to hear a lot on the AP exam when an object is rolling. So that means that as it's moving translationally, it's also spinning. So for example, we have a soccer ball that's rolling across the field. So when the soccer ball rolls, it's moving rotationally and translationally. Conversely, if an object is sliding, this means that it's not spinning at all. So an example would be a hockey puck, a cylinder just sliding across the ice without any rotation. So what causes rolling without slipping? So let's look at a combination of the two types of motion, the translational motion and rotational motion for a bowling ball rolling across the floor. So we have the bowling ball rolling, and if this was just moving translationally, it would just be sliding. All of its mass would be moving in the same direction. So if we look, the center of mass is going to be moving with the velocity of the center of mass. But because translationally there is no spinning, all the mass is going to be moving at the same speed. It's like a box moving across a floor. So the velocity of the center of mass is what's going to be the value for each of any mass at any point on that ball. Now, if we look at what's going on with it rotationally, that would be as if it's just spinning and not moving anywhere. So it's just spinning and rotating, as we can see there. And now, when you look at it again, when the object rotates, we can see the top moves to the left with a velocity of the tangential velocity, which is angular velocity times the radius. And the bottom is going to be moving to the right, which we define left as positive, so right would be negative, so the tangential velocity would be negative omega r. Now, if we just add the rotational and translational values together, that's going to give us the rolling without slipping effect. So let's look at what this means. So if we add rotational and translational to our bowling ball, what we're going to do is we're just going to add these vectors. The top vectors point the same direction, so that would be a combination of the two vectors. We would just add those together, and we'd end up with the velocity, the tangential velocity being much larger, and we know that the velocity of the center of mass for a translational equivalent is going to equal the angular velocity times the radius for the top of the bowling ball, translationally and rotationally. So that means the top's going to be moving with twice that tangential velocity. The center of mass, we only have one vector pointing in the center of mass, so that's still going to have the same velocity. The center of mass does not matter if it's rotating or not, it's going to have the same translational velocity. Now the tricky part, what causes rolling without slipping? We have these two vectors that are pointing in opposite directions and have equal values. So if we add those together, it actually gives us a velocity of 0. So that means at the bottom where an object is rolling and there's contact with the ground, there's no velocity at that point, which can be kind of tricky. But remember, when an object is tossed up in the air, it has a velocity of 0 at the highest point for just a brief moment in time. And that's what's going on here, is that the velocity at the bottom is 0 for just that brief instant, like an object being tossed in the air and returning to the earth. So the highest point, the velocity is 0 for an object being tossed, rolling without slipping, the velocity is going to be 0 at that point in time. And this is what causes rolling without slipping. So what does cause rolling without slipping? That's friction. Friction causes rolling without slipping, and specifically static friction because the bottom of the ball has no motion. So remember from our forces unit on Newton's laws that static friction is the friction before something starts sliding. So that means there's going to be no motion at all. With no friction, the ball would only move translationally. So it'd be like sliding on ice. If you've ever tried to drive on ice, your car rolls with slipping. So that's what driving on ice is that there is no static friction or minimal static coefficient of static friction, which means that an object can spin, but it's not going to move as easily. So what effect does rotation have on kinetic energy? Well, the total kinetic energy, we have to do the sum of the rotational kinetic energy and translational kinetic energy. And we could substitute the equations in, the one we derived for rotational and the one we know for translational. So 1/2 I omega squared plus 1/2 mv squared. And of course, we would know that the larger the rotational inertia of an object, assuming that it has the same velocity of the center of mass, that means the larger the rotational kinetic energy. So let's put this into application, something that I call the Great Race. So what is the Great Race? Well, we have a ramp, and at the top of the ramp, we have some competitors that are racing to the bottom. The competitors are the sphere that's rolling without slipping, a cylinder also rolling without slipping, a box that is moving and sliding down the ramp without friction. And then we also have a hoop that is moving down the ramp by rolling without slipping. The question is, which object will reach the bottom first? Or will it be a tie? So let's go ahead and start this race. On your marks, get set, go! And we can see the box is our blue ribbon winner. Our second place is the sphere, third place is the cylinder, and last is the hoop. So naturally, the next question would be, why is this the order of the finish? So let's first take a look at this video of a actual live finish of these four objects. In this case, we use a car rolling to the bottom of the ramp. So you can see in that video that the order of the finish, doesn't matter the masses of the object. All that matters is that the type of object. So the car was moving translationally. The sphere, cylinder, and hoop were rolling without slipping. So what we're going to do in this is we're going to calculate the final speeds of each of these objects. And the speed, the faster it's moving at the bottom, that means that the less time it took to get to the bottom. So to calculate the speeds, we're going to use conservation of mechanical energy, which means we're going to draw energy bar charts. Now, if you are watching this video and not one of my students, we did a video earlier on drawing energy bar charts, and we're going to go through the bar charts rather quickly, so you can click the link up above, and that'll explain to you how to draw energy bar charts. So we're first going to do this for the box. So we define our system. For the box, we've done this situation many times. We have UG, the Earth gives energy to the box, which is kinetic energy. We substitute the equations in and solve for the velocity of the box, and we've derived this equation many times. The velocity of the box is the square root of 2g delta y. Let's look at the calculations for what came in second, the sphere. So this is going to be a little different. So we start with the same. We have UG, the Earth gives energy to the box, but we have translational kinetic energy, and it's not moving as fast at the bottom. So what accounts for the extra energy, because there's no energy lost outside of our system, there's no work done. So the fact that it's rotating, that it's spinning, is the variable that we're missing. And now we can see that the rotational kinetic energy plus the translational is going to give us that initial gravitational energy. So from this point, we see that translational is smaller because it's rotating. So that's why the sphere does not get down to the bottom as quickly as the box. So we substitute the equations in, and then for the rotational inertia and angular speed, the rotational inertia of a sphere is 2/5 mr squared, and angular velocity is v divided by r, so we can substitute those in. But we got this messy equation. But if you look through each term, you can see that each term has a mass value. And that mass value is just the mass of the sphere, so that's going to cancel out. And if we look all the way to the right of that equation, we've got an r squared at the end of our rotational inertia equation. But we also have that r on the bottom of our angular speed equation. But that's squared, so we can cancel those out as well. So let's clean this equation up and then solve for our velocity, simplifying the fraction, combining like terms, and we get that the velocity of the sphere is equal to the square root of 10/7 g delta y. Now 10/7, that's not the same coefficient that we had for the box, that's different. So we're going to come back and look and compare the final velocities of the sphere in the box. But let's first do this for the cylinder. So we're going to go through this one a lot quicker. So we've got our system, same UG, but now the translational is not as large, so there's more rotational kinetic energy. And as we substitute in and cancel things out, we can clean that equation up for our conservation of energy, so we can finish solving for our velocity. And we find that the velocity of the cylinder is equal to the square root of 4/3 g delta y. And that 4/3 coefficient is different from our previous with the box and sphere. So lastly, let's do this for the hoop as well. So again, going through this rather quickly, the hoop was moving slowest at the bottom, so it's going to have the least translational and the most rotational. So we can, again, go through, substitute our rotational inertia equation, cancel out masses and the radii from our equation, solve for the velocity, and we get that the velocity of the hoop is equal to the square root of g delta y. So why were the results of the Great Race where they were? So let's look at the velocities of each of those. And we can see that each one has a square root of g delta y. The only difference is the coefficient that is in front of g delta y. So we compare the values of the coefficients in front of g delta y, and we know that 2 is greater than 10/7, which is greater than 4/3, which is greater than 1, which means that the velocity of the box is greater than the sphere all the way through to the cylinder. So the faster the speed at the bottom, the less time it takes to reach the bottom. So the velocity of the box is going to reach first, then the sphere, cylinder, and the hoop. And this explains the results of the Great Race. So let's take a look at an example problem. Example problem, we're going to consider two objects. The first is a box that slides without friction. So the mu of k is equal to 0. And the second is a sphere that rolls without slipping. Now, both objects are going to have the same translational speed, which is key to this question. Is it would be different if they did not have the same translational speed. And the question is, which object ends up higher on the ramp, or do they just reach the same height? So the way we're going to answer this is through energy, but let's first take a look at the results. So we can see the box slides up, the sphere actually goes higher than the box. The box does not reach as high of a point as the sphere goes higher. So the question is, why is this? So the way we're going to find this is by drawing our energy bar chart. So we have translational kinetic energy changing to gravitational energy for the box. So the translational kinetic energy is equal to the UG, which is going to dictate the height in which the box reaches. So how is this different for the sphere? Well, the sphere has the same translational kinetic energy, but remember that it's rolling without slipping, so it also has a rotational kinetic energy, which means that if it has a rotational kinetic energy, that we have more energy to begin with because the sum of those two kinetic energies is equal to the final, which is UG. So the fact that the object is rotating and has rotational kinetic energy means it's going to have more gravitational at the end, which means that it's going to reach a higher height. So we take into account rotational kinetic energy along with translational to account for the sphere having more overall energy. That's because they're both moving translationally with the same speed. So this is an introduction to rotational kinetic energy. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below and subscribe to my channel, Happy Coaches, and follow me on Instagram and Twitter at Happy Coaches.